Mats.
So today we are incredibly proud and very much looking forward to listening to Professor Julia Herzen from Technische Universität Munich. And she have written a number of seminal papers on phase contrast imaging, and I think many of us read them, but it's different, of course, to hear it from the source, and you have the possibility to ask questions. And Professor Herzen is active in Technische Universität Munich, which I would say have almost created the field of phase contrast imaging. Maybe somebody will be very angry if I say that, but to a very large extent, and with Franz Pfeiffer and collaborators now somehow scattered over the world, but you are still in Munich, Julia. So it will be great to listen to your lecture. So please go ahead.
Yeah, thank you very much for this kind introduction and also for the invitation. I'm very happy to be here. Let me start sharing my presentation with you. And then, so I hope you see the right slides. Okay. Yeah, my name is Julia Herzen. I'm an assistant professor at the TU Munich and mainly working on biomedical imaging. And it's my pleasure today to share with you some ideas and some recent results that my small research group is working on. So I'm a part of a larger group, as Mats told already, of Franz Pfeiffer, who's one of the pioneers, I would say. So he is working pretty long already on the field of phase contrast. And so it's also, I'm very lucky to share some labs with him and have access to a lot of machines that we have here on site. And today I will present you what I'm focusing on and yeah, give you some ideas. And I'm happy afterwards to discuss anything that you have as a question. Let me just start to introduce my small group. So it's a research group of biomedical imaging physics. It's around about 10 people altogether, master students and bachelor students, which are quite often changing. But I have 5 PhD students in my group and a postdoc here, Lorenz. So we are working on our mission. And this is mainly taking the X-ray physics, so imaging science and technology. And this image here shows, maybe well known for all of you, the interactions of X-rays with matter and bring them close to the application. So help biologists, medical doctors to solve the problems based on the modern developments in terms of X-ray physics. And these new technology or novelties, and you might also be aware of what the novelties in the X-ray physics are, but I would say from my perspective, it's mainly the multimodality, which happened, I would say in the last decade, really increased and is standardly used now at all large-scale facilities, but also in the labs, becomes more and more available. And what I mean by multimodality is that you're just not just looking at the transmission of the X-rays or the attenuation, purely the reduction in the amplitude, but also in the phase shift, so tiny refraction angles, which also happen if your X-rays transpass a material, which is described here by this complex refractive index. I will come to that in a few seconds. And one of the easiest methods is this propagation-based method, which I will also briefly explain later. So you illuminate your object with a coherent illumination, and then you just propagate the beam until the detector, and you see all the influences coming, the effects coming from the refraction at the edges of your sample. And the second novelty, which I also trying to use and include into these collaborations with the biologists and medical doctors, is the spectral aspect. So that in terms of the attenuation, you then have access to two different effects of the interaction. It's the photo effect and the Compton effect in the range, energy range, which is interesting for imaging. And the total attenuation will be a like linear combination of these two contributions, photoelectric and Compton effect. And this is well known and used for several years already, and also found now the way into the clinics. But there is also another term, or you can also use the spectral aspect in terms of the phase shift, of course. And I will show you some aspects of that if we use both the multimodality and the spectral aspect, how we can go beyond just taking morphological images, to just take nice images, but also get some information out of it. So really some quantitative numbers. And let's start from the very beginning. So you all know the history of X-rays, discovery of them 1895 by this gentleman here, Conrad Wilhelm Röntgen, and this very famous the hand of his wife as the image. And the first Nobel Prize in physics for this discovery. And since then, I would say this novelty is still using mainly the aspects that already Röntgen tried to find already for this first publication. So he looked for both attenuation and phase effects, but he couldn't measure the multimodality actually. So these phase effects he couldn't measure because he doesn't have the technology for that, but nowadays we do have. And this is mainly used for gain contrast for soft tissue without contrasting it. And this will be one of the one part of my presentation today. The second part, which I would like to talk about, is the multi-scale imaging. So that means that we would like to perform studies, imaging studies on whole organs of, in this case, small animals like mice or rats, down to cell level, and how this can work in combination of different sources and methods. And the last point is, which is really important to me, and this is the quantitative imaging. That means going beyond just taking images, but increasing the accuracy and allow for material decomposition. So without putting any assumptions on your specimen, you really can decompose in the material decomposition, and how you can use the aspects of X-ray physics for that. So let's start with the first, the multimodality. And this is mainly, I will only talk of phase contrast here, not other also possible signals like scattering. Let me explain what I mean with multimodality in terms of phase contrast. So in visible light regime, we know that we have the bright contrast, so the attenuation on the left. You see the fibroblast, and the visible light, which is hardly give you any contrast in just the transmission. But if you switch or push buttons of any good microscope, in this case here, for example, the size microscope, you can gain some information on the phase shift, which is caused by the sample. And so these tiny refraction angles that you use for the contrast generation. There's also one of the pioneers was Fritz Zernike with his Zernike phase contrast, also a Nobel Prize in 1953. Of course, we know that similar effects happen in the X-ray regime. So attenuation, we have an object which we described with the complex refractive index, and we know that the imaginary part will be responsible for the attenuation, which is used in the clinics mainly at the moment. So you have the Compton and the photoelectric effect, which is I already mentioned. In the energy range, which is interesting for the clinical and the biomedical applications. And for the phase contrast, it's the real part which causes these phase shifts. So your object is actually changing the direction of the propagation by a very tiny angle alpha here. And this is then the phase shift, which is needs to be detected. And there are plenty of different methods in the last decades developed. The very first method is the so-called crystal interferometer. This was the very first demonstration by Bonse and Hart experimentally that this is working, that you can really detect the phase shift in an X-ray regime. So these are like single crystal interferometer by like etched in silicon, and used the Breck reflection is used here to separate the beam in two paths, and one is the reference beam, and the other one contains the sample, and afterwards they interfere again, and what you measure is directly the phase. It's a very sensitive method. It's detects the phase directly, as I mentioned, and one of the first demonstrations. Then one very common method, but I think it's more and more less used at the synchrotrons, is the so-called crystal analyzer method. It's trying to detect the refracted angles here, the refractive intensity, by like shifting a silicon crystal by an angle, actually. So performing a measurement once with and once without the sample, and then everything which is then refracted by the sample will be will come as an intensity at the different angles. So you will be able to sort this and get the first derivative of the phase detected. So it's also a method which was used many times in former times from the 80s starting, but now I think there are much more easier ways to get the phase detected. And one of the mostly used, I think, that if you go around the world to all these large scale facilities where you get the coherent or brilliant illumination, and even in the labs, you have this kind of phase contrast method, which is taking over, I would say, which is the propagation based. So you do not need any optics, no crystals and anything. What you need is a coherent illumination. Means your X-rays coming here needs to have the ability to interfere. So mainly coming maybe from a very small source. And what you then do is you propagate your beam after the sample to certain distances, and then you can see the effects and edge enhancement due to the refraction happening at the edges of where the refractive index is changing in your sample. This method is measuring the second derivative of the phase, and is then also less sensitive than the other two, but very simple. And the method that I would like to talk more about is the one that I was working mainly on, is the grating-based method. And I will tell you a little bit about that, how this works, what you can expect from that, where are the limitations of this method, and also the potentials regarding the advantages, maybe, because this, obviously, you see, you need optics for that. It's also measuring the first derivative of the phase, but these optics, of course, make it more complicated than just the propagation-based method. Well, it was developed as all the phase contrast methods at the large-scale facilities. So you see here two of the sources that I'm frequently using, the one in Grenoble, ID 19 imaging beamline at the SRF in Grenoble, and one in Petra 3 in Hamburg, where I'm engaged with a long-term proposal at two imaging beamlines. Like trying to get even further development of that. And I will come to it a little bit later to present you some recent results from these sources. But of course, this is also possible to use in the lab. With a standard source, due to exactly the person that we mentioned in the beginning, Franz Pfeiffer. He actually had an idea to how to get these optics working with non-coherent sources, and the trick that he applied was to introduce an additional optical grating, which actually creates small coherent slits, or increases the coherence of one entire source spot, and it's just enough to illuminate the very important grating. In this case, it's the phase shifting grating in the middle, or very close to the sample. Just few periods of it with these with the coherent illumination, and then it will overlap at this detecting area here at the. But I will come to this on the next slide to give you an idea how this works. Actually, slightly not to go too much into details, but We have, in principle, at the synchrotron, you need an optical element. In this case, it's called phase grating here. So it's a structure which is most of the time etched in silicon. It's a 1D structure, like bars, holes, bars, holes. And these bars, they are selected such that they shift a special energy coming from the X-rays by a special amount. The phase is shifted by a special amount, adjusted to the design energy, we call it. And what it does, this phase grating, is when the X-rays, without any sample, go through this phase grating, they form in a special distance d due to the Talbot effect. It's a self-imaging effect, an interference pattern here, which then you can analyze with and without the sample. And so this interference pattern is, of course, only formed when all these conditions are fulfilled. So you have so all the energies, the design energy fits. So it works perfectly, of course, only for or ideally for monochromatic X-rays. But of course, also we can apply it for a broad spectrum with some reduction of the quality. What we see in this, I will show you also how we do that and what results we get in the polychromatic case. Okay, then in this case, the X-rays come from the synchrotron, so they are coherent and monochromatic. They are forming now this interference pattern. And this interference pattern is way too fine to be resolved by a standard detector. So it has the period either the same as the phase grating, which is like 2 to 5 or maybe maximum 10 microns in period. So you would have to use either a very highly resolving detector, and then your field of view will be really limited. But if you want to scan like a full mouse or even patients, so human, then you need to be more independent from the detector size or the resolution. So you take a standardly used clinical flat panel here with 150 to 300 microns resolution. And with that, you now need something to resolve this interference pattern. And this is this so-called analyzer grating. You can imagine that or you can think of this grating as an array of slits. So you create a slit by filling the gaps here with something highly absorbing. So it's in our case, it's gold. So it very efficiently absorbs X-rays, so that you have really an array of small slits. And with this slit, actually, you try to move over one period of your interference pattern and detect the average intensity in 1 pixel. So this is how you get images out of that. Without the need to resolve this interference pattern directly. And of course, the phase shift that you measure, so you perform this scan here, the analysis of this interference pattern once with and once without the sample, and then you compare, and with that you get actually the phase shift and related to these refraction angles alpha out of this. So to give you an impression what images you can get of this, so the multimodal information is here, a box with sunglasses. We scanned this in radiography with such gratings, and you see the transmission here. This is the standard, corresponds to standard radiography that you know also from the dentists. You see mainly the highlighted, the highly absorbing materials, like here the metal parts, and also a little bit like enough contrast for also for plastics. And there is something slightly visible, but not really clearly visible what it is. And this might help to look into different other, the different signals from this modality. And if you now look at the refraction, you see that you should see two main aspects. One aspect is we are obviously only sensitive in one direction. So what we measure is the gradient of the phase just in one direction. This means we use a 1D grating, and of course only perpendicular to this grating we are sensitive to this signal. So we could overcome this by using a 2D grating, but this would make it even more complicated. At that time, we have some solutions for that. I will also come back to that. And the second aspect that you see here is that the contrast for these low absorbing parts, the plastic parts, is much better than in this image here. And this is why mainly phase contrast is also used for low absorbing materials and soft tissue to increase the contrast without any need to contrast the material by any high Z materials, for example. So, and the last signal which we also can get out of this data analysis, so from the same set of images, we generate these 3 images. So we performed, as I hope you remember from the last slide, we performed this scan of the analysis of the interference pattern. And from this analysis, we calculate these 3 images. And the image comparing the reduction of the visibility of this interference pattern gives us the dark field, the so-called dark field, which is a number describing the small angle scattering, which happens if you have a very inhomogeneous object. So your refractive index is changing several times on the way through the sample on a microscopic scale. So you can't resolve that. It's much smaller. It's in the range of the periods of your gratings, like 1 to 10 microns. And it changes very strongly. Then you get actually this strong scattering signal. We call it dark field in this case. And you see what then really pops up in the signal is the tissue, which is in this box, hidden in the box. Okay, but we're of course not using this method to look at sunglasses. We look at biomedical samples. And this is one of the I would say very early images that we got at the ESRF when the grating interferometer was installed there for the first time. And this is a tomography of through the abdomen of a mouse, which is fixated in formalin, so ex vivo. And on the left, you see the conventional micro-CT. So you still can recognize some inner organs here, but the contrast is rather low, because of course the mouse is fixated in formalin, so everything is you see actually rather low contrast because everywhere there's the formalin. And at this on the right you see exactly the same reconstructed slice, but now the phase shift is used as a contrast mechanism. And you see what happens is actually that you really increase the contrast for soft tissue just by using these different quantity. And what you see, what physically is now visible on the right is the distribution of the electron density, while here is mainly, depending of course on the energy that you use, is mainly the mass density that you see there, or this like with higher Z you also can increase the contrast here. Okay, now let's come to the second part, and this is the how can you use this approach now for multi-scale imaging? So perform studies to scan full organs or even maybe whole mice down to cell level. And there are some challenges which we need to address. And first, we started to increase the throughput. Actually, is a good idea to bring this method in, or to try to do this in the lab and not always at the synchrotron. So the image that I showed you from the mouse was from the synchrotron, but actually it's not an option to perform studies if you have to apply for beam time. And so you need something in your in the basement, I would say. So we have installed one. And our first setup was built in 2012, and I show you some first results, which definitely show that it's obviously more challenging to get nice images out of this method in the lab. So this is a mouse, again, fixated in formalin without any staining, and this is the phase contrast image that we got after the machine was installed. We used a rotating anode, a very old rotating anode with a molybdenum source, some gold gratings and silicon gratings, so 3 grating setup for the lab, and a detector, a photon counting Pilatus detector, which is from the company Dectris. And this is what we got. And actually, you see that it can't compete with anything that we get from the synchrotron. So we started trying to understand what is going on there. And the main aspects that we had to improve is all the contributions that come from the polychromaticity. So as I mentioned, you create or you design this optics for one special energy. And once you increase the polychromaticity, because you go for like standard X-ray source in the lab, things might go wrong. So if you do not take care of what you're doing and do not understand where all these artifacts come from, you end up with bad images. And so it took us several years to understand how this works, and then we significantly improved the quality of the images, as you can see. So this is again a similar mouse, stored in formalin, and it's again the phase contrast which we scanned here, and this is now very comparable from the sensitivity, from the image quality that we get. So sensitivity, what I understand with that is these very small, tiny refraction angles that we can detect are very comparable to what I showed you from the synchrotron. So you see this image, this was the previous one from the ESRF. And on the right is now the image that we got with our setup after 4 years of improving and optimizing. And now the only thing that changed or is different is the resolution. So the resolution at the synchrotron is, of course, if you scan the full mouse, like 20 microns, and here we are around 100 micrometers due to the large source spot and also large pixel sizes and so on. So, but the possibility to perform this phase contrast imaging in the lab with this high contrast was already really useful to perform several studies on some diseased tissue with medical doctors together. So we published some work on arteries with plaque, where we really, so these are human arteries. All images are showing phase contrast, so there's almost no contrast in attenuation, because all these samples are stored in formalin, and then you get almost no contrast for them in attenuation. So that's why I'm not showing these images along with the phase contrast here. So what we did is we scanned arteries with plaque and quantified and also classified the plaque there, because also looking for dangerous plaque, which is the soft plaque containing different lipids and solutions in it. We looked at different liver tumors, and here also in kidney tissue with tumor, and published that. And just to tell you that this is a huge field of view compared to what you can get at the synchrotron, and this is actually like 3.5 centimeters. This is a Falcon tube where we had a large amount of tissue, which is significantly giving you a statistics for a huge tissue. But of course, it's not, the resolution is still not enough to see. So we are not coming to the cellular level. Yeah, and we just see the structural changes there, but we do not see the individual cells, of course, not at 100 microns, and also some features are also lost in that. So we now my PhD student Josef Scholz and my postdoc Lorenz Birnbacher, they started even improving with some technological improvements, and where we are now is compared to the 2016, we now have the 2019 even more improved the image quality, mainly using now much more detectors with a higher efficiency. So we do not use a silicon photon counting detector, but some detectors with smaller pixel sizes. It's now a Centis with cadmium telluride and 75 microns. We have a new rotating anode with a much smaller source spot, but still the same, almost the same flux. So we improved several things, and of course we also understood a lot more about the gratings and how to adjust them to the given energy and the given spectrum. And now we are at about 40 microns resolution in our lab. But the bad news about that is we need almost 1 day of measurement time. So for this tomography, of course, it covers a significant amount of the abdomen of the mouse. So it's like in total, I think we can cover up to 5 centimeters in height. So the full mouse and then 5 centimeters in height at once. But still you need a full day, like 24 hours for getting a full tomography of that. And if you think then you have to scan 10 mice, then you're busy more than 1 week with that. And that's why we try to improve that. especially for some studying on carotid arteries, which we, of course, with 40 micrometers, we can see much more details than we could see with 100. But here, so you see on the left, small calcifications here, and also changes really in the vessel wall. You can see much better. But this one-day measurement is really an issue. So Josef is now already almost finishing his PhD, and we are also, he succeeded in reducing this down to 11 hours. So we can, without any compromise on the image quality, and that's the same quantitative. So you see the distribution of the electron density, and the sensitivity is the same. Just by optimizing all the components such that you now can also scanning with procedures which are not stop and scan as like step and shoot, but everything is continuously rotating and so on. So all these optimizations are done now, and we are ending up something with around 11 hours, which is still pretty much, but for a micro CT, so any one of you who's working with a micro CT will know that for a high resolution and high quality scan, you need to scan at least several hours. Okay, let me come back to the synchrotron imaging. So I told you that now we are able to scan full organs or even the whole mouse in the lab with high contrast. And but we still do not see with 40 microns, it's you can't see any cellular level. And this would be interesting to go to even higher resolutions, maybe down to 1 micron. If you look then into some human tissue, then the cells are sometimes larger, like up to 20 microns, and then you really can see on the cellular level this imaging. And then now the method that I presented to you, so these gratings were developed at the synchrotron, but if we now go back to the synchrotron, try to perform high resolution imaging, we recognize that things change because the phase contrast is now just accessible by the standard propagation, as all the sources, if you go to Petra 3 or ASRF, they are highly coherent, highly brilliant. So it comes with any measurement, with any full field picture, you have automatically the phase effects. And now what is interesting is that, of course, you need to retrieve the phase. So this is an image showing you a stained mouse kidney. It's one tomographic reconstruction, it's showing the transmission, exactly, so the attenuation image in that, and scanned at 20 kV at a very short propagation distance. But still, what you see is that the contrast only at all the structures is actually, you get an edge enhancement. This is due to the propagation effects, which I mentioned already. So you illuminate it with the coherent radiation, and all changes in the electron density or in the refractive index give you this high contrast. So this high intensity at all the edges gives you maybe higher resolution, but not the contrast that you expect or need to have. So as I told you, now what you have here is a mix of a transmission and the phase effect. So you need to perform some processing to get it out, to get the phase information out of it. And the mainly used in processing is the transport of intensity equation. This is there is a method which is called Paganin algorithm, which puts some assumptions on your sample, and it's mainly that it's contains or is composed of a single material and is weakly absorbing. And if these two assumptions are not applicable, and in the case of a stained mouse kidney, it's not, you get really severe artifacts. And just to show you what you can get out of this Paganin phase retrieval, you see that this image is actually containing not the information that I would, the resolution is gone, so you have a huge smearing here, huge blurring, and you do not have any distributions here, so you do not have a quantitative image, let's say. So you can't tell why it's bright here. Is it because it's really the feature of your object, of the kidney of the mouse, or why it's bright there. So it's really absolutely full of artifacts. So you need a method which is working without any assumptions, and you can imagine it's gratings, so as I presented, do so they can extract the face without any assumptions, but still they need some adjustments here, and I will come to it in a few seconds. Just to explain you what I'm talking about when I talk about staining. So previously I tried to convince you that we do not need any staining, so we just take samples. They are just stored in formalin, and without any staining, we can produce contrast in face. So why do we look now at staining? And this is why, because we have a group which is developing specific staining for soft tissue. So I have a colleague, her name is Madeleine Bosse, and she is looking into staining for X-rays, which is, I think, the staining itself is old. The idea is old, that you drop your sample into something with containing high Z materials. Mainly in X-ray regime, it's iodine-based contrast agents which are used. But what happens is that these contrast agents are non-specific. That means they just go everywhere, and just depending on the tissue density, maybe, so how dense is your tissue and how heterogeneous it goes inside or not, and sometimes also some chemical processes, maybe treatment of your sample prevents the stain to enter the sample. But if you scan now a mouse kidney with the attenuation contrast with the standard micro-CT without staining, you get something like that. And what Madeleine is working on is she looks into different staining procedures which are used for histology. So the standard histology in clinical perspective, so the pathologists are using, they are well described, they are well known, and you can also very specifically stain a special feature or special type of a cell organelle. For example, if you take the standard H and E, so hematin and eosine stain, which is used often in the pathology or histological stains, then it's well known that the H is going into, or is highlighting the cell nuclei, and the eosine is highlighting the cytoplasm. And exactly this you can also do with this eosine and hematin, but just if you take the same procedure as for the histology, you will not see any contrast for X-rays, as this is not highly absorbing enough. And what Madeleine is doing is she modifies it by putting more high Z material into one molecule. So up to 3 bromine atoms here more than in the standard eosine procedure, for example. And with that, she gets this mouse kidney stained specifically, so really highlighting the cytoplasm of this tissue, of the cells, such that you really see a very nice resolution also, but also the contrast that you get is not just, of course, you can generate such contrast also with other like iodine, but this is a specific one, and this is just the beginning. So she's looking into different other types of staining, which are highlighting the collagen fibers, for example, because there's a full bunch of different stains available from the histology, where you can try to modify them and use them for 3D in X-ray imaging. But this explains you why we're now looking at stained tissue. So we had this kidney that I showed you that we couldn't really retrieve the face out of it because it's now stained. So we corrupt actually the assumptions of a homogeneous and low absorbing material for Paganin. And now we propose a different method to overcome this, and this is high sensitivity imaging, which we now set up already at the imaging beamline PO5 at Petra 3. And what we do there is we use a 2D phase grating. So I told you the grating that we normally use is a 1D structure. Now we use a 2D structure, which produces you an intensity array that looks like that. So dots, which are like 2D dot structure. it mainly focuses actually your X-rays in these small dots. And with that, we can again retrieve the attenuation and the refraction. Of course, also the scattering, but I will not go into detail here. But this attenuation and refraction, by again comparing how your sample actually distorts the distribution of your dots in 2D. And this is what I'm doing at the imaging beamline PO5 with the PhD student Mirko Riedel, who is working with my colleagues Jörg Hammel and Felix Beckmann at DESY, and some collaborations where we would like to apply it from cardiovascular diseases or also pathology and biologists in that. And I would like to share some results with you. So you think of the stained mouse kidney that we tried to retrieve the face. It's on the right using the Paganin, so the standard propagation-based, and on the left, it's called now SBI. So this is the abbreviation for speckle-based imaging. That means you have these small speckles and then you track how they are distorted. And you see that it's obviously working. So we can retrieve the face here. This is the distribution of the electron density of this stained mouse kidney. And the resolution, so for that, we just looked into one small zoom in into this tissue that we have here. And then we analyzed the resolution in this scan. And here we achieved the resolution of 3.1 micrometer, which is already very close to the resolution of the imaging system, but still a little bit too or less than that. But what is impressive is the electron density resolution that we get here. That means what small differences in the electron density we can retrieve with this method. And here we measure this as the standard deviation inside the embedded material. And this was the paraffin or wax. And this is 1.599 electrons per cubic nanometer. So if you have a change which is larger than that in electron density, you can retrieve this with the face. Oh, I'm very sorry. Just a minute. So, okay. So, but I told you we are not close. We are very close to the resolution of the system. It's approximately 1.5 microns at this beamline. So we try to even get higher with the resolution in the scan. So we scanned an unstained human kidney with a larger piece of it to extend the field of view. It's now instead of just fitting 5 millimeters, we have almost 1 centimeter in it of tissue, and scanned it with very small pixel sizes, stitched it together, and then reconstructed, and achieved the special resolution of 1.6 micrometers here. Okay. With that, I would like to come to my last point, and this is the quantitative imaging, where I would like to convince you that it's very interesting in imaging, not just to take images, but also to look into the quantitative numbers, because it not only increases the accuracy, but also the comparability, because if you then go to another machine and measure your sample there as well, you know what you get. It's not just like a convolution of several artifacts of produced by a special method, but really a quantity which is dependent on your sample. For example, the distribution of electron density. And this is what I showed you already. So this the attenuation in the using the spectral aspect in the attenuation, you can distinguish between the photoelectric and the comptoelectric distribution that is present in your image. And this is constantly used already in the clinics. And this is shown for 2 different materials here. For sure, you know that it's element specific and energy dependent. So for aluminum, for example, you have the photoelectric contribution is less than Compton for a special energy. And if you go to a higher Z material like iron here, then the photo effect becomes even already at the same energy, much higher is the contribution of the photo effect increases because it's a highly Z dependent, like Z over 4. Here you have actually the Compton contribution. So if you can distinguish that, you get actually the contribution of the photo and the distribution of the Compton effect. And as I mentioned, it's frequently used in the clinics, as you have the different workarounds before the spectral detectors were available. We had these 3 different, like QVP switching by GE, or dual source by Siemens, just giving you the ability to measure at 2 different spectra and to distinguish between photo and Compton contribution. And the Philips machine, for example, is having a dual layer detector, where the lower energies are detected in the top part of the detector and the higher energies in the lower. And this is the machine which my Dr. Pfeiffer is my cooperation medical doctor at the clinics, and she explained or gave me this nice example, which is very convincing, which I would like to share with you. What is dual energy or quantitative numbers helping at the hospital, and why this is interesting. So she told me actually that if a patient comes with an emergency and is scanned with a CT, then a conventional image would look like that, which is already containing a contrast agent. So the patient was given a contrast agent, and what this machine can do now is calculate a so-called virtual non-contrast image. You see this on the top, and at the same time, of course, the iodine map density. And this is just by the ability to distinguish between the contribution of the photo and Compton effect for these 2 different materials, for the patient, so for soft tissue, and for the iodine, actually. So now you do not have the need to scan the patient with and without contrast agent. So if the patient comes to the emergency room, they just directly give the contrast agent and scan him or her in this dual energy CT, and can directly distinguish between iodine highlighted regions and the natural, so the non-contrasted part. They can calculate the so-called mono-energetic images, so how your patient would look like at 40 kV, for example, because you will never be able to scan your patient at 40 kV. And also interesting aspect, you can calculate the Z effective distribution. So really, where is your iodine went to? And this Z effective, for example, is also used for calculating radiation in the oncology, like radiation plans for treatments and so on. So Z effective is a now commonly used numbers, the distribution for that. And just one of my last aspects I would like to mention is, you remember this image I showed you, the conventional micro-CT and the phase contrast image from the mouse. And what you do in dual energy CT is actually measuring 2 different quantities, photo and Compton effect. In this case, we also do 2 different quantities. We measure them separately. We have the conventional micro-CT, which is, of course, in this case, at lower energies, maybe dominated by the phase, by the photo Compton effect, by the photo effect, sorry. And the phase contrast is mainly giving you the distribution of the electron density. So 2 different quantities. And this is just, if you plot now, or you perform a scatter plot, you plot the attenuation coefficient mu on the y-axis and refractive index decrement on the x-axis, you get a scatter plot. And just by the basis transformation away from this vector space, which is spanned by mu and delta, you can transform the basis to 2 different other materials. And in this case, you have then material 1 and material 2 distribution by this change of vectors. And this we tried at our synchrotron that we have in Munich. So we have a compact light source, which is also producing quasi monochromatic light. And we scanned a chicken heart in this case with some iodine, which we included in a small container here. And by just performing a tomography with the gratings, so grating-based imaging, we had generated the attenuation image and the phase image. So this is shown here on the top row. And with this information, these 2 different information in place, we can actually generate the Z effective image. We can generate the iodine image, which you see here. It's a small dot here. This was the tube filled with iodine, and the non-contrasted image. And then, of course, these monochromatic images at different energies, which you can also generate from the dual energy. So this was the aspect showing that we can also do that. And of course, if you do not have any contrast agent, you can also do that with different materials. And this is a decomposition in 2 different materials. This is a piece of pork, which contains like muscle tissue and fatty tissue, and you can then use as this vector material the lipid content and protein content. And by applying this to such a mouse, you can see that if we use then this is the reconstruction of the face. On the right, we have the attenuation, and we use this to decompose into lipid and protein. You really have this in 3D. So the distribution of your lipid, you have this on your 3D data set, and the distribution of protein. And then, of course, you get the rest, which is there as the formalin water mix in this case. And of course, we can also generate the effective atomic number. In this case, it's rather boring because we only see the bones, and this is the highest Z that we can see from the mouse, as this is not stained and do not contain any contrast agents. But still, it's a quantitative image. So with that, I would like to finish. So of course, this is a method which generates you quantitative numbers, and I would like to go for that as also at different levels. So I showed you our efforts to get this close to a cellular resolution, and this would be interesting to look into the quantitative imaging at all levels. With that, I would like to sum up. So I showed you the potential of multimodal quantitative biomedical imaging on these 3 different aspects which we looked at. We looked at the multimodality, especially with the grating-based method, giving you the possibility to measure in the lab, but also at the synchrotrons. I showed you some multi-scale imaging approaches that we can scan whole animals in our laboratory downstairs, so pre-screening at like moderate resolution, and then go to higher resolutions at the synchrotron, where we can scan very small objects down to 1.5 or 1.6 micrometers. And the quantitative aspect, which is from my perspective is the most interesting part, that you really get information on the distribution of different materials, which are of interest, rather just nice, only generating nice images. With that, I would like to thank some colleagues, which of course support me at the synchrotron, especially. This is the Helmut Sander-Hirium and Daisy, my group at TUM, and also the Franz Pfeiffer's lab. And special thanks go to Professor Thibault. Pierre Thibault is one developing this processing package for this kind of imaging that we use at the synchrotron, and some funding agencies, and of course you for your attention. Thank you very much.
Thank you very much, Professor Hertzen. This was certainly very, very interesting. So now is a chance to ask questions.
I have a question.
Yes.
My name is Olaf. I'll turn on my video. It's nicer.
Hi, Olaf.
Hi, Julia. Nice to see you again.
Yeah, nice to see you.
So I have questions about this grating-based phase contrast.
Mm-hmm.
Like first, what energy were you using in those images with your source?
Do you mean the monochromatic case or the polychromatic in the lab?
The polychromatic in the lab.
Okay, so
maybe both.
Yeah, both. Okay, so I show you. I just go back to this. This is the standard setup. So on the left, on the right, you see the images, how we can get them from the rotating anode now. So we have a molybdenum source, which it's a Rigaco. I don't remember exactly the name of it, but we run it at 50 kVp. And we do not use any filtering, but the gratings actually filter it already. So you have 2 gold gratings in it, in substrate. So we actually do not see almost nothing below 15 or rather 20 kV. So the spectrum is between 20 and 50 kV. Now we optimize the gratings for 35 kV. Before we had like 27, but this was due to the detector, which was less sensitive at higher energies. So we used this Pilatus in 2016, and this was like 1 millimeter silicon, and it was almost blind at above 30 kV. So we had rather lower design energy, and now we have a cadmium telluride detector, 75 microns from Dectris, and this is now very sensitive and efficient, even at higher energies, and that's why we now push a bit the design energy of the gratings, and it's now to 35 kV. But this is the setup that we use for the highly sensitive measurements of phase. If you're interested more in the dark field, for example, there we have setups running at rather higher energies. So we have a prototype of a patient scanner at the clinics, which is really scanning the full patient, the lung of a full patient. And this is running at 70 kV peak or 80. You can adjust, and has a field of view of 40 centimeters.
Is there a certain energy which you think is, or an energy range where this method is more applicable, or maybe it has to do with the gratings also?
It's actually so that there is so as we use both in the lab, or if you go to the synchrotron and use a 2 grating interferometer. So once you need the gold grating, any energy where the gold becomes transparent doesn't work anymore. So everything below 40 or 50 kV peak or kV works fine. And then there is a gap up to the absorption edge of the gold, which is around 80. And after that, you have again a good visibility of these gratings, like around up to maybe like 80 to 100 to 120, and then it's again dropping. And this you can overcome. So at the synchrotron, we are now applying this 2D grating. So we do not use any gold gratings anymore. We just use one phase grating. And this is very easy to create for rather low energies. And if you go to higher energies, you need maybe a different material than silicon. Because what we have is like a period of 10 microns or 5 microns. And if you think of the design energy of 20 to 30 kV, then you need maybe something around few tenths of microns in silicon. Or you go to the same gold, for example, then you maybe need only a few microns of gold for that. So it's again easy to fabricate.
The phase grating is not the problem.
Yeah. And if you go for phase grating alone without any analyzer or a coherent source, then you can overcome these difficulties of the like that your gratings are transparent.
Okay. Thanks. So you think that what's the limiting factor sort of for your visibility here? Is that still the gratings, or is it the source size? Or
yeah, I think so. The question to answer this question for the polychromatic case is more complicated, because there it strongly depends on what you set up. So there is the periods matter. So what rather do you go to smaller or larger periods, distances, in which Talbot distance you go, detector efficiency. So how efficiently do you see the contributing energies, and do you see also the others? And yeah, the amount of your spectrum matters. So what we do is now really simulate it before and adjust this to your application, because you will not have one machine which can everything. I think if you have something where you are interested in soft tissue, I would rather go for lower energies and design something higher with a higher sensitivity. But if you're more interested in material science and samples which maybe should not be measured in the fluid environment, then I would maybe build something less sensitive, and for that maybe more flexible at higher energies. But now what we do is really simulating, putting the real measuring the spectrum, putting it into that, and then simulate the whole process.
Right. Yeah. Thanks, and thanks for a nice presentation. Very, very clear.
Thank you.
Nice to see all the results.
So I have been allowed to extend a few minutes if we have some more questions here. If it's okay with you, Julia.
Yeah, it's fine for me. So sorry to be ahead of, of my schedule.
Hi, Julia. This is Michael Burleson.
Hi, Michael. How are
It's
you?
really nice to see you again.
I just stopped sharing. Sorry, then I can see you. Hi.
There, hi. So unfortunately, I missed the first part of the talk because I misunderstood when the meeting was going to be. But I have some related questions similar to Olaf's. So when it comes to these gratings, it seems like, as far as we understand now, these gratings create the biggest or has the biggest impact on the visibility. If you go to higher KVs, like you said, there is like a region where they become transparent, and that really affects the visibility that you get. And visibility has a strong impact on like the noise in the images and the signal light.
Yeah, not only. It's actually a mix of also the number of photons. So the flux is also very strongly influencing. So not only the visibility, what we recognize is actually changing the rotating anode. We're now working at a higher energy. That means a broader spectrum. Yeah. This dropped the visibility. So before we were working at higher than 30 in the lab. Mm-hmm. So these images I showed you from 2016, they were taken with a very high visibility in the lab, like 30 kV, 30%. Mm-hmm. And we thought that this might be the best option to get this very high resolution visibility. But once we increase the spectrum or make the spectrum broader, we also recognize that these photons, so we had more photons, and the visibility dropped to approximately 15%. 15. But now we have 15 in the lab, but we have the sensitivity, so the number of or the quantity, how good we can resolve different electron density changes is even improved, because we have more.
Even if you go down, okay, interesting. And then you went to, that was 50 kV, right?
It's 50 kV peak, so it was optimized to 27 kV. So the whole grating, the phase grating was built for 27. Now we replaced it also for 20 to 35.
So for this 50 micro, or for the 50 kV setup, how thick are your gratings? Like, and what's the aspect ratio of the gold gratings? What's typically, not easy to manufacture, but if you like really push the process.
Yeah,
it's can you make?
Yeah, so I always, so we're using the gratings from from KIT, so KIT in Karlsruhe, and they have a company where they sell. So everything that is easy to get, let's say, or what is standardly working, there is a company called Microworks, and they are offering this to manufacture. And I think what they easily can do is something. So if you do not need the aspect ratio to be very high, so you're not going to very high energies, then maybe like 100 micron thick gold might be enough. So for this 50 kV, this is definitely enough. So 100 micron height of the gold bars is enough to create a good visibility. And then it depends on the period that you aim for. So they can create easily 100 micron height for 5 micron periods, for example.
Oh, that's 20% aspect ratio.
Yeah, it's pretty high. Yeah.
Okay.
This is actually X-ray lithography that they use at the synchrotron.
Okay.
So you can't do this with etching so nicely, because then it's not homogeneously, and this is really sensitive. So I really can see any instability or change in homogeneities in the periods. So if I etch something in silicon and this somehow distributes not perfectly, you can actually directly see the changes in the image.
Okay. So let's see. Another question. So the thing that limits how big samples you can image, is that limited by how big gratings you can do?
No, this is no. We have now the patient scanner in the clinics, where we can scan the full, like the lung of a patient. It's like a 40 centimeters. So we have actually a scanning machine, which is scanning from top to bottom the lung of a patient in 7 seconds. And the only limitation is you can actually use them as a tiles. You can stitch them together. And this is what we did, because you will have also to bend them. So once you're, because once you create or you put your gratings with a high aspect ratio in the beam, and if you do not bend them in the fan beam, then you get shadowing effects very fast after maybe 2 centimeters. Right. And to avoid that, you can bend them. So nowadays we bend them, and this is easy on a field of view of like 7 centimeters round. You can easily bend the grating. But for this large field of view, we really put the tiles on like an arc. So they were flat, but we put them on an arc. Cool. And then stitch them together as good as possible, so that you do not see large gaps. And this worked pretty nicely. So if you like, I can send you some links to the recent publications on that. Yeah, and the major limitation is how large your sample can be, is at what energy you can create these gratings. And the lung is, of course, something which works fine because it's almost transparent. So you don't need like 120 kV peak, but it works at 70 or 80, but it definitely would be a challenge to go even higher.
Yeah, so on the detector side then, so if you have these bent gratings for the, so you're talking about a setup on a, well, if you have a lab setup, then you're gonna have kind of a spherical setup, right?
Yeah, but any set, so if you're not talking about synchrotrons where the beam is parallel, but you go for any laboratory source, you have always either a fan or a cone.
Right, but so you do this trick by bending them or stitching them. What do you do on the G2 side where the detector is? Does that create a problem that you have a flat detector then?
No, so you need to bend, of course, all the gratings. Yeah. So you bend all 3 gratings, and the only thing that what we use in this patient scanner is a flat detector. It's different for a CT, of course. In the CT, you have already this on an arc, so you don't have to care about that. It's only the reconstruction. It's a problem for the reconstruction, so that you know where exactly the path that your X-ray travel, and then you can adjust it to get correct reconstruction. For this, the projection imaging, this doesn't matter so much. So because the image creating part is the entire set of the gratings. So the last gold grating gives you actually the interference pattern, which you then just project on your detector. And once this set of gratings is in the correct bend, so all the radii are correctly met, then you can actually align everything perfectly, and then you see a homogeneous distribution of your intensity on your flat detector.
So, okay, I've taken a lot of time here, feels like, but so we've done some basic modeling of this just to try and understand the technique and things like that. And it just seems to me that if you could just improve the visibility in your fringes, you gain a lot by, the dose that you don't have to put into.
Yeah, definitely. Yeah.
So if it pays off so much to have greater visibility, why don't you always push to get like the thickest possible gratings? Is that, you say like, 100 micron is enough.
No, it's a good question, because it's first it's for the higher energies we tried. So there's this aspect ratio. We have I think periods around 10 microns, and there is at least 250 microns gold in it.
Okay.
But what you start, so you can't push it much further, because it becomes inhomogeneous. So what you start then becoming are strongly. So this is an electroplating. What you get. So they use X-ray lithography to etch these structures, and then to fill them with gold, they use electroplating of gold. And this process can't go infinitely high. So there's a limit where it becomes then not homogeneous enough. And you can imagine if you then especially combine this with spectral resolving detectors, and you have an inhomogeneous amount of gold on your on your gratings, then you of course change your spectrum dramatically, and then it makes your this is a huge mess of calculating the so really getting a quantitative image out of it is then complicated.
Mm-hmm.
But this is I think there are a lot of research going on to go away from gold, because this is also a main limitation. It's pretty expensive in larger field of view.
Yeah.
So I think what the manufacturers try, I know it at least from Philips and Siemens, that they are trying to look into this. They are also using the anti-scatter grid out of tungsten. So they try to somehow reuse this methodology, how they create these anti-scatter grids to create gratings. But I don't know how far it is already, as they of course do not publish anything. So, it's hard to tell how far it is, but I think the more people looking at
3D printed in tungsten actually, but it's hard to get to the accuracy that you are used to, still competing with the KIT spin-off company.
Yeah,
but I think that is basically in FDA approved products today.
Mm-hmm. And getting rid of the gold would also, if you increase the coherence of your source. So if you go for these Exilum sources, and I saw these very promising results on this high power source that they will, I don't know if it's already on the market or just the first tests. I talked to Emil Espes, and he said that they really strongly improved its high power machine.
They announced something quite recently.
Mm-hmm. This might be an option, but I don't know how far they are away from rotating the source around the patient. Maybe it might take a bit.
I don't know either. But do you remember Per Takman?
Yeah.
Yeah. So he still works there.
Ah, okay.
Excellent. Yeah. Just, you know.
Okay. Any more question, Mikael?
Well, I feel like we should let her go.
We can maybe discuss in a separate meeting.
Yeah. No, I'm just curious to learn as much as we can.
Shall I send you a Zoom link and we can discuss directly afterwards?
You know, that's an excellent idea actually, and then that's perfect. We will like to you obviously already know each other, but we like to to network here, as they say. So that's a perfect idea.
Okay.
Yeah, I appreciate it, Julia.
Thanks.
Thank you so much.
You're welcome.
Yes, thank you
very much. It was a great talk.
For arranging.
Thank you very much, Julia, for joining MedTechLabs with this lecture. Thank you.
Thank you for inviting me.
Thank you again. You made our day. Cheers.
Cheers.
Bye-bye.
Bye.